In this chapter, we will be using calculus to find the extreme values of a function. In this video, we will be looking at more maximization and minimization problems.
All right, everybody. So now we're going to take a look at some more maximization, minimization problems here. And this one is a classic one, okay? A wire of length L, okay, and sometimes you'll be given a number there, but you don't really need to. You can just state the letter L as the length here. Is divided into two parts. Okay, one is used to form a circle, and the other is used to form a square. And again, you don't have to stick with these shapes either. But just this is the most common way to approach this problem. Okay, how should the wire be cut so that the total area formed by those two shapes is a minimum or a maximum? Now, this is a unique problem in that you are not being told whether you're going to be maximizing or minimizing the result here. So you actually need to do a little bit more investigation to figure out, well, what did I actually find here? So let's just take a look at the problem here. So let's start with a bit of, wire here. So this is our length L, and we're going to cut it. Now, the issue is, how do you cut it? Okay, how do you cut it? So what we're going to do here is let's just put a little mark right here. And let's say that this distance right here is x, and this distance right here is going to be then, as a result, L minus x. Okay? Now, I'm going to put, in this particular version of this problem, I'm going to put part of this towards a circle and part of this towards a square. It doesn't really matter which one I do here. Let's just say, for example, that this is going to be the circle, and then this will be the square. Now, bear in mind that because I'm using this wire here and these pieces of the wire to build these shapes, what I've got here is x is actually going to be the circumference of the circle. So I know that whatever circle I get here, x is going to be equal to 2 pi r. Just like this L minus x, this bit of wire right here, when I bend it to form the square, that L minus x is really just going to be the perimeter of the square. Okay, and let's just say that, just to give us a little bit of context here, here's my circle with a radius r. Here's my square. Let's say that it's got the sides of length n, just to throw a variable at that. So what that means here is that L minus x is going to be equal to 4n. Okay? So x is the circumference of the circle. L minus x is the perimeter of the square, which would be 4 times the one side length. Now, if I'm going to come up with an expression for the area, okay, the combined area of both of these shapes here, I need to figure out what the radius of the circle is, and I need to figure out what the side length is here. Because remember, the area of a circle, the area is going to be pi r squared, and the area of a square is going to be just the side length squared. But it turns out that's relatively easy to do. Because of these two expressions here, I know that r is going to be equal to x over 2 pi, and I know that n here is going to be equal to L minus x over 4. So that's a pretty easy transition to make here from the circumference pieces to an expression for the two parts, the two variables here that I need to get the area here. Now I'm going to put those into my formulas here. So this will be pi r squared plus n squared. But now this will be pi x over 2 pi squared plus L minus x over 4 squared. Okay. So now I've done the substitution, and now I've got an expression for the area just in terms, okay, just in terms of the variable x. Remember, L is a constant here, and pi is also a constant. Now I am going to simplify this just a little bit here. I'm going to get pi x squared over 4 pi squared, and I can see right now they're going to get some canceling there with the pi's. Now over here, with the L minus x squared, when I look at that, I think here, well, maybe I should expand it, maybe I shouldn't, maybe I should just leave it, because I'm going to take a derivative here in a moment, and I can just use the chain rule here. But maybe what I would do is I would just take and make this L minus x squared over 16. I'll just leave it like that. It doesn't really matter. It's not going to make a difference in a moment here. So what I'll do here is I'm now going to take the derivative of this expression. Now, bear in mind, one of the pi's canceled. I'll bring down, I'll bring down a 2. And the factor of 2 that I bring down will cancel with that 4 in the denominator. So this will end up being x over 2 pi. Over here, this is going to require the chain rule, so I'm going to bring down the 2. 2 will cancel with the 16. Also have an 8 down there. This will end up being L minus x. But then I've got to multiply by the derivative of what's the inside function here. And the derivative of L minus x is just going to be -1. And actually what I'm going to do with that, because I'm kind of lazy here, and I can do this in that one step here, I'm just going to make the expression here negative. All right. Good. There we go. Now, I am going to take my derivative now, okay, as I do with these maximization problems, minimization problems. I'm going to set this equal to 0. Okay, and I'm going to determine, okay, for what value of x this derivative here is equal to 0. Okay, now, there's a few things that I could do here to make my life easier. One of the things I'm going to do right now, just to make my life a little bit easier, is I'm going to multiply this whole expression right here. Maybe I'll put brackets on the whole thing. I'm going to multiply this by 8 pi. Mostly because I just want to get rid of the fraction just for a moment here. It's going to pop back up in a second here. But for the time being, I know that most people here prefer to think of it through this way. 8 pi times 0 is just 0. That's okay because it's an equation. I'm fine with that as long as I do multiply both sides by 8 pi. When I multiply this expression here by 8 pi, I know I'm going to be left with a 4x, and then the pi's cancel. Over here, my 8 is going to cancel. I'm going to be left with pi multiplied by L minus x, which is a fair bit easier just to look at here. So this is 4x minus pi L plus pi x is equal to 0. I'll bring that over. So this is going to be equal to, let's make it L pi. It just looks better if the L comes first. I don't know why, but it does. And I'll take out the x here. So this will be 4 plus pi is equal to L pi. And so x is going to equal, L pi over 4 plus pi. Okay, and there we go. So that is the value that, though I don't know whether it maximizes or minimizes this particular expression here. I do know that this corresponds to a maximum or a minimum value. I just don't know which one it is here. Now, that's not hard for me to determine, and in fact, I can kind of reason this thing through right now, and I'll show you why. Because at this point right here, bear in mind that this is going to be quadratic in terms of x, and this is also quadratic in terms of x. But more importantly, notice that the coefficient here of the x squared term would be positive, and it would be positive over here too, because when you expand this binomial, okay, you're going to get a negative x times a negative x. When you expand that out, you're going to get a positive x squared term here. So essentially, this is a parabola that opens up, meaning that what I've just found here is the x coordinate that corresponds to a minimum. Okay, now I can figure that out by taking, for example, the second derivative and plugging that in. I could also figure this out another way, and I'll show you another way of doing this right now. If we take a look at our endpoints, we're going to get lazy here. Essentially what's happening here is if I investigate my number line, okay, if I investigate my number line here, I've got L pi over 4 plus pi, let's say right there. Now, what I'm interested in is how this function is behaving, or what I should say is how the derivative is behaving at these two endpoints, at the two natural endpoints for this particular question. Now, we haven't brought up these endpoints yet. Now's kind of the time that makes perfect sense for this. Bear in mind right from the beginning here that I could have put that x, anywhere I wanted along this length here. Okay, x, I could have squished that in In fact, I could have squished this x in and made x equal to 0, in which case L minus x, this whole bit here, would have gone towards the square. So it's like taking this part right here, and I'm going to make that L minus x the whole thing. Or I could have made x way out here, basically made it equal to L, and said that the whole thing is going to the circle. Basically, I have the ability to put however much I want on the circle, however much I want on the square. So there are some natural boundaries here. The value of x could go as small as 0, in which case this means that the whole thing is square. Or it could be up here at L, in which case the whole thing is going to the circle. So there are some natural boundaries here. Now, I'm going to use that because this is imposed by the problem, but the formula doesn't really care about these particular endpoints here. So I'm going to use these endpoints here to help me figure out what's going on. So I'm going to go to my derivative here, and I'm going to plug in x equal to 0 into this. Okay? If I plug x equal to 0 into this term goes away. That goes to 0, and I end up with a negative L over 8 as my slope, meaning that the slope is negative over here. Whoops, sorry. If I plug L into it, okay, if I plug L into my derivative here, this becomes L over 2 pi, and this becomes L minus L over 0, which disappears, and I get a positive here. So if I check at 0 and I check at L here, I notice that the function decreases and then increases. So the function here is decreasing. Okay. Now, in terms of the scenario here, let's say it's going to be decreasing on the interval from 0 to L pi over 4 plus pi. Oops, sorry, not union. Not union, this is quadratic. And increasing on the interval L pi over 4 plus pi, comma L. So I know that this corresponds to a minimum. So as long as we cut this off such that this distance right here is equivalent to the total distance times pi over 4 plus pi, that will give us a minimum. Now, the next question was asking us for the maximum. Okay. Now, that happens as a result of these endpoints. So I want you to think about what's going on right now. We'll come over here. So what I've got here is I've got a parabola, okay, that's doing something like, I don't know, like this. I'm not entirely sure quite now. Here's 0, here's L, and this right here is that L pi over 4 plus pi. So it's a parabola that opens up here. The only possible points that could give me a maximum would be either one of those endpoints, because it's a parabola that opens up. That's the only way that I could get this, because I've discovered that there's no other local maximums or minimums. This is the only one, so that leaves only the endpoints for possible maximum or minimum values. So let's check them at the endpoints here. Let's check at x is equal to 0. What do we get for my area? Well, let's come over here. Whoops, sorry, right here. If I let x equal to 0, this term disappears, and I get L squared over 16. Okay? Okay, fine. Let x equal to L. That's my other endpoint. Now, if I let x equal to L, this goes to 0. This is going to become L squared over 4 pi. So area will become L squared over 4 pi. Now let's just take a quick look at this. We're going to compare these two areas here. This is 16. Now bear in mind that pi is a little bit more than 3, but not closer to 4 here. So that means that 16 is going to be larger than 4 pi. And bear in mind that as the denominator gets smaller, the overall fraction gets larger. So it turns out here, this is the scenario that gives me a maximum area. And in fact, my diagram here kind of hinted to the fact that I knew that was going to look like that. So anyway, there you go. Okay, kind of a complicated problem here, but a good problem because it doesn't lead you, even in the statement of the question, it doesn't lead you to a conclusion about whether it's a maximum or a minimum. Once you've got this bit of information, you really do have to do a bit of an investigation to see what it is that you're actually looking at. A wonderful problem. All right, now here's another fairly commonly asked problem here. A rectangular poster has an area of 6,912 centimeters squared. Now, that's the entire poster, okay? The side margin is 8 centimeters, and the margins at the top and the bottom are both 6 centimeters. We want to find the dimensions of the poster, the overall poster, that maximize the printing area. Now, this maybe needs a little bit of a diagram to describe what's going on here. Okay, so we've got our poster here, and this right here is the printed area. And we want to maximize that shaded bit right there. The dimensions, or sorry, the area that we're given is the area of the entire poster here. So what we're going to do here is, let's call this X, let's call this Y. And so the information that we're given here tells us that 6,912 is going to equal to X multiplied by Y. At least that's what I gather from that. Now I'm interested in what those dimensions are, what X and Y are, that maximize this area, given that we've got these margins here. Now the margins have caused some confusion to students in the past here, just because there's a bit of a misread on it. The side margin is 8 centimeters. That means this distance here is 8, and this distance here is 8. The top and bottom margins are 6, which means this distance here is 6, and this distance here is 6. So now our formula, because bear in mind, we're trying to maximize the printed area, so our formula for the printed area, okay, will be length times width. Now, the length here is going to be Y, but less 6 from the bottom, less 6 from the top. So it's going to be Y minus 12. Okay. The width is going to be X, but less 8 from the right side, less 8 from the left side. So X minus 16. So now this is our expression for our area. Now, and that's okay, but I've got two variables in there, and I'm a little lazy. I would rather it only had the one variable. Now, because I've got this expression right here, I really could, really and truly, I could just take the derivative of this, but then I'd also have to take the derivative of this and do a substitution in there. So I can either substitute later or I can substitute now, and I think most people, and most teachers, when they teach this, most people are going to substitute in. They're going to find an expression for either X or Y, and they're going to plug that in. And I know most people, when given the option, they are going to find, or they're going to isolate for the Y there. And that's okay. We'll do that. There's no reason it has to be the Y. We could very easily get rid of X in this expression, but I get it. I get it. So our area here will be 6,912 over X minus 12. Okay, multiplied by X minus 16. Now, I'm going to take the derivative of this, and I could do it in a couple of different ways here, but I think what I'm going to do first is I'm actually going to expand that out. So 6,912 over X multiplied by X is just 6,912. Okay, 6,912 multiplied over X multiplied by negative 16. Well, I'm actually just going to do that on my calculator here real quick. Whoo, and that's a big number. That's going to be minus 110,592 over X. Keep distributing, minus 12X. And then I'm going to get positive 12 times 16, and it'll be positive because those are both negative there. This will be positive 192. I didn't actually have to do that because I know what's coming up here in a second. And I know that when I multiply those two constants together, I'm going to get a constant, and that the derivative of that constant will be 0. And actually, that's what's going to happen right now. The derivative of 6,912, 0. The derivative of negative 110,592 over X is going to become positive 110,592. 10,592 over x squared. Okay, because remember, this is like dealing with x to the negative 1, and so when you bring down the exponent, those will cancel, and we'll get negative 2 there. And then this will become negative 12, and then the derivative of 192 is just 0. Good. Now I've got the derivative with respect to x. I'm going to set that equal to 0. Start my solving process here. There are two terms. I'm going to get rid of the term that doesn't have the x in it. I'm going to move the 12 over. Now I'm going to get rid of the rational expression here too. I'm going to multiply through by x squared. And I can do that so long as x does not equal 0. But I think that's pretty safe to say that in this scenario here, we are excluding that particular option here where x is equal to 0. So that's not a big worry here. Now I'm going to take that 110,592, and I'm going to divide that by 12 to get 9,216 is equal to x squared. Now I'll take the square root of that. Now I'm assuming that that's going to work out to be a nice number, and it does. I get plus or minus 96. Now, I know, and you know, that it can't be negative 96. That doesn't make any sense in the context of this question. But if your teachers are like me, when you're working through the algebra, I want to see that you recognize when you take that square root here that there are two answers here. Now, granted, I also want to see you reject the negative root here, but I do want to see that you recognize that there are two options there, okay? So that just tells me that you really do understand the algebra that you're doing here, okay? And granted, I know you're thinking, oh, come on, it's just positive 96. Yeah, but if you separate the context from this, it could have been positive or negative. It's only the context that actually forces you to grab that positive 96 out of that. Okay, so find the dimensions of the poster paper that maximize the printing area here. So the x here is going to be 96 centimeters, so it's going to be 96 centimeters by, and then I would take 6,912 divided by 96 by 72 centimeters. Okay, and so those are your two values here. This is your x, and this is your y right there. Now, bear in mind that sometimes the way the question's asked is they ask it from a different perspective here, where they give you the, let's say, the printing area, okay, and you want to maximize or minimize the entire area of the poster here. Basically, the difference in that question is really here, like y plus x plus. That's the difference. Another version of this problem might ask you to not just give the dimensions of the overall poster, but the dimensions of the printed area, in which case you would have to subtract 12 from the y, subtract 16 from the x. So other things that could happen with this question just to make it a little different. Anyway, I hope that makes sense. It's a good problem. Okay, let's take a look at another problem here. A boat leaves a dock at noon and heads west at 25 kilometers an hour. Another boat heads north at 20 kilometers per hour and reaches the same dock at 1 p.m. When were the two boats closest to each other? So we're trying to minimize the distance between the two boats closest to each other. Now, I freely admit that when we start to work with problems like this, I always got to take a moment and make sure that I am thinking this thing through correctly, because when we went through a chapter on related rates, we look at problems that look sort of similar to this setup here. In related rates, though, I am okay with there being like an x variable, a y variable, a z variable, and I'm just taking the derivative implicitly. Here, though, I'm looking for when were the two boats closest to each other. So what I'm looking for here is time. Okay, and that's pretty standard with these maximization and minimization problems. That's actually, even if they didn't ask when were, if the question asked what was the closest that they got to each other, really I would probably still have to figure out when that occurred. So let's just draw this out here. So the first boat leaves the dock at noon and heads west. Now, heads west. Based on this right here, that's this way. I've seen so many students swap the west and the east. Okay, just bear in mind what that means. Not that that would have really affected the question here, but it does look a little bit goofy when it says go west and you start drawing it to the east here. So, and this boat here is going 25 kilometers per hour. Now, at the same time, another boat heads north and reaches the same dock at 1 o'clock. Now, that is giving you some information here. First of all, if it heads north and reaches the same dock an hour later, that means it must have started down here. Don't start it at the same dock and go north here and think, oh my gosh, this question doesn't make any sense. Well, yeah, because it doesn't say that it starts at the dock, it ends at the dock. So it starts down here, and the second boat goes north. Okay, now it's going north at 20 kilometers per hour. But I'm given one other bit of information here, that an hour later, that boat reaches the dock. Now, if it traveled 20 kilometers an hour for an hour, we know that it was 20 kilometers away from that dock. So it was 20 kilometers south here. Now, we're going to create a triangle here between those two. And what we're interested in here is, let's call this Z here. We're interested in minimizing the distance between those two. So let's zoom in a little bit here. Okay, we're interested in minimizing that distance. Now, here's my triangle. Now, for some time, at some value of time here, we want to figure out what the distances are in this triangle. Now, this one here is pretty straightforward because it's going 25 kilometers an hour for t hours. So the distance it's gone is just going to be velocity times time. Not a big deal. This one here is a little bit more complicated because this is the actual distance that the boat went. So this right here is 20 times time. But that's not the distance that shows up in the triangle that I'm drawing. Okay, that I'm drawing here. This is the distance. Well, I know that that distance right there, from my finger to my finger here, that's supposed to be 20 kilometers. And this is 20t. So this bit right here must be 20 minus 20t. So now I've got the two legs of this right angle triangle. So if I want to figure out when they're closest to each other, I'm going to use the Pythagorean theorem. So I know that z squared is going to equal 25t squared plus 20 minus, oops, I know I'm running off here, 20t squared. Okay, and there we go. Maybe I'll zoom out just a little bit. Oops. Okay, now I am looking to minimize the variable z here. So I could throw a square root on that, but I'm not going to. And that's just out of sheer laziness. I like the way that kind of looks here with the z squared, and I'm comfortable taking the derivative of z squared implicitly with respect to time there. Okay? I don't have a problem with that at all. And it turns out actually that's not going to be an issue in a second here at all. Now, I also could expand out everything here. I really could, but I've found that most students don't want to. They'd rather just take the derivative right now and kind of see what falls into their lap. They're sort of hoping that's going to simplify the scenario here. So let's just jump into it. Let's just take the derivative. So the derivative of z squared here will be 2z, and I will use dz by dt, okay? It's going to equal 2 times 25t multiplied by the derivative of what side? Inside here, the 25. Now don't forget about that. Please don't forget about that. It's so easy to just get stuck on this little bit right here. Okay? I know that you bring the 2 down, but forget about the derivative of what's inside there. Now let's move on to this term right here. This is going to be plus 2 multiplied by 20 minus 20t. And then again, I have to multiply by the derivative of what's inside there. Whoops, sorry about that. Which would be negative 20. Whoops, I'm running right off the paper there. That's okay. Negative 20 there. Now, I am going to divide. So I'm going to make this dz by dt. I'm going to get dz by dt by itself. I am going to divide by 2, and that's okay because all those 2's will cancel. I'm totally fine with that. And I'm going to divide by z. I'm not thrilled about that, but actually that's not going to be such a bad thing here. So there's going to be this z in the denominator, but you'll see that that won't be an issue here. 25 times 25 is going to be 625. Whoops. Wow, 625. I don't know why I did that. 625t. And this is going to be minus, and I'll just distribute that through the 20 here. So it'll be minus 400 plus 400t. Great. And now remember, the next thing that I do is I'm going to set this equal to 0. Now the reason why I didn't mind dividing by the z there is because I've got this rational expression, and what I'm going to do right now is I'm going to multiply this entire rational by that z. Now I'm not so worried about this right here, but when I multiply that by that z there, it's going to disappear on the left-hand side, and it's going to disappear on the right. That z there is actually kind of irrelevant. And so now I'll add those two t terms together, and this will become 1025t. I'll bring the 400 over, is equal to 400. So t is equal to 400 over 1025. Okay, well, whoops, sorry, you can't see that. Now, that's fabulous. That's wonderful. What a great result here. That's not particularly useful to us. So what I got to do here is I'm going to convert this into a time that's actually useful to us, because the question is asking, when are the two boats closest to each other? Well, remember, time is in terms of hours in this problem, and I know that because I'm given speeds in terms of kilometers per hour, okay, kilometers per hour. So this has got to be in terms of hours. So when I take 400 and divide it by 1025, I get that as my time. But please be really careful with this. That right there does not mean that 39 minutes went by. Time is not metric. What I got to do is, once I get the decimal here, I'm going to multiply by 60 to convert that fraction of an hour into minutes. And so what this means here is basically between 23 and 24 minutes, little over 23 minutes here. Okay, this is when the two cars were closest to each other. I could do a little bit better if I want by subtracting the 23, because that was 23 minutes, and then convert that fraction into seconds by multiplying once again by 60. So essentially, at 23 minutes, 25, when I round that, 25 seconds later, okay, that's when the two cars are close. Sorry, the two boats, cars. It's the boats we're talking about here. So they are closest at 12, 23, 25. 12 hours, 23 minutes, 25 seconds. All right, this question here is another classic. You will bump into this question in some form or another. Now the scenario might change, but the description, the geometry of this problem is just really, really a common problem. So this is a really good one to spend a bit of time on. So here's the question that I've got here. A man is on an island 4 kilometers from the shore, and we assume it's a straight shore. He wants to get to a restaurant located L kilometers down the shore. Okay, now that's not L kilometers from his island. It's L kilometers. Like if he was to go straight to the shore and go L kilometers over, that's where that restaurant's located. Now, he can row at 3 kilometers an hour, and he can walk at 5 kilometers an hour. So where should he land his boat to minimize his travel time? Okay, where should he land his boat? So here's what the scenario looks like. Here's the straight shore. Here's where he's located, okay? And the distance to the shore is 4 kilometers. Okay, so this is him. This is on his island here. Now over here, this is the restaurant. So here's home. Here's the restaurant, okay? And this distance right here is L. Now, he wants to know, where should he land along the shore to minimize the amount of time that he takes traveling? Now, this question, by the way, this is kind of maybe a weird sort of a scenario to throw on it. But that's just because what we want is a really posed question that you can work on, that you can use your calculus skills to solve here. But this has got great applications in all sorts of different places. But one of the ones that I find so fascinating is its application to optics and refraction, okay? Because when light travels through an object, it takes the path that minimizes its time as it goes through. Anyway, not that we're going to get into that, but that's a really neat application of this particular idea here. Now, just to make life easier, let's say that this distance here is x, and so this distance here will be L minus x, okay? We know that he travels along here at 3 kilometers per hour, and he's going to travel along here at 5 kilometers per hour. Now, the implication here is that it would not be the fastest to simply row straight there. That's probably because he's using his least efficient method of transportation for this entire distance. Now, nor would it be efficient to row straight across and walk this distance here, because although he is more efficient at walking, you're giving him like the maximum amount of distance to do that in. Somewhere in between, there's a nice compromise between those two. So here's how we determine this. The time that he takes, and this is what we want to minimize, okay, is going to be, now I want you to think about this, time is distance over speed, okay? Now, this part right here, well, that's easy. That's easy right here. The distance that this guy's going to go, and I'm just going to put this off to the side here, is going to be, L minus x over his speed, 5. And I'm going to add that to the distance that he rows over 3. Now, what is the distance that he rows? Well, it's a right angle triangle. I know that the one leg is 4 kilometers, and this other leg I've called x. So I know, using the Pythagorean Theorem, that that distance there will be the square root of x squared plus 16. Okay? And so here we go. This is all we need. Now I'm going to dive in and I'm going to take my derivative. So the derivative of t with respect to x, and I'll just use t primed here. This is going to be, first of all, the 1/3. That's the denominator that I've got right now. This will end up being 1/2 x squared plus 16 to the negative 1/2. Okay, that's because the exponent here would be positive 1/2. I would bring that down, subtract 1. Multiply by the derivative of what's inside, 2x. Now, over here, if I distribute that 5 to the two terms in the numerator, I get L over 5, and then I get negative x over 5. Well, the derivative of L over 5 is just 0. The derivative of negative x over 5 is going to be negative 1/5. Okay, now, that turned out pretty nice. There's a little bit of a mess here, but it turns out actually this is going to end up looking fairly nice here in just a moment. So what do? I take and I set my derivative equal to 0. Okay, now this is going to cancel. The 2's are going to cancel right there. And just before I start to solve this, I am going to move the 1/5 over. And I'm going to simplify this a little bit. I'm going to be left with x over 3 root x squared plus 16. Okay? So now I'm going to cross multiply, essentially. So I'm going to make this 5x is equal to 3 root x squared plus 16. I've got this square root there, and so I gotta square both sides of the equation to get rid of it. I don't want that there anymore. Now, right here, this is where when I'm teaching, I will tend to spend a little bit of time and focus my students' attention, because this is one of those spots here where I've seen students that get the big idea, but then will make a little mistake here, and it gets really frustrating when everything else makes sense, but because you make a little arithmetic error, it's hard to anyway. It's hard to feel you're really successful here, especially when you make those little errors here. So what you're going to do is you're going to square both sides. So the left-hand side's not a problem, becomes 25x squared. On the right-hand side, that square root is going to cancel the square is going to cancel the square root. So you get x squared plus 16. But you got to remember that that 3 is also being squared, so it's 9 multiplied by x squared plus 16. So this becomes 25x squared is equal to 9x squared plus 144. I'll bring that 9x squared over, which will get me 16x squared is equal to 144. I will divide, and 144 divided by 16 is going to be 9, which means my x could equal plus or minus 3. Now again, I know, not negative 3. Okay. In fact, negative 3 really doesn't make any sense. If you go back up to your diagram, negative 3 would look like putting it over here. And the guy's really going the wrong way here. That doesn't make any sense at all. So I know the negative 3 doesn't make sense. But again, if I'm like a lot of your teachers there, I want to see you recognize that that is algebraically the next step. But in the context, that doesn't make any sense. And so he should hit the ground 3 kilometers over. Okay? 3 kilometers over from straight across, that's the distance that's the position in this diagram that's going to minimize the amount of time that he spends traveling. Really good question. There are other variations of this that I've seen. I've seen it where it's a lifeguard trying to figure out where should I jump into the water to minimize the amount of time spent rescuing. Now, by the way, if a lifeguard ever stops to do that kind of math, not a very good lifeguard. I've seen other variations of this diagram here where you're trying to get utilities across a river and then along a shore to get to a residential zone there. Lots of different things you can do with it. Basically the same idea. Just if you haven't seen this question yet, I suspect it's coming.